Hello, welcome to Guessing the Methods exam part 6. Now last year I guessed it, but this year it's my past students. They've got their own tutoring company. I'm going to click that link. When I do, I end up at this wonderful website, and I love this Join the XCV team. If I click on that, maybe I can get a job next year. That would be awesome. Alright, that's enough of that. On to the first question. Have a try at it, see how you go. Alright, super simple question here, but one that if you don't know what's going on, you've got a problem. So, when it comes to probability density functions, it doesn't matter what the shape of it is, could be look like anything, but the area under the curve must be equal to 1. So that's what we're looking for with these options. So I don't think there's much for it. I've just got to type in my options and see if they work. So there's one function. If I integrate that function, now when I integrate the function, I need to integrate between the domain specified. So 0 to 1. Okay, and it looks like the area under that curve is 1. So I think maybe my answer is A. Just mucked around my view window to show it. A little bit worried though, because maybe it's one of these other answers as well or something. So maybe I'll just take a look. Typed in 1 on x squared, sketch that. I'm just going to G-solve that. I'm not going to do this for all of them, so you don't have to watch me do every single one of them. Between 1 and 2. Alright, the area under the curve there's 0.5, so no good. Now this is part C, f of x equals 1/2. I integrated between 0 and 1, that's the domain, 0.5. No good either. Last one, and that's sine x between 0 and pi, and we can see an answer of 2. No good either. That means my answer is A. What do we take away from this? Well, we take away that fluency with your calculator, being able to work quickly with it, is going to be really important in the Tech Active exam. Learn how to use it. Alright, celebrating, next question. So it looks like we've got another sort of calculatory question here. Have a try first. Alright, we've got two functions, and we want to find the area bounded between them, and find out, like, between what bounds is the area closest to 1/2. So enough talking, let's just sketch those two on our calculator. So I've typed them both in there, and I'm going to draw that right there. Okay, so I'm just going to sort of zoom out a little bit. Now looking at all of our numbers, the lowest number there is like -1. The largest number is like 1.23. So you can be a little bit strategic with your view window here. I'm going to put an x minimum of like -1.1 and an x maximum of like 1.5. Alright, so that's really the thing that we're dealing with, right? Now, I think option A looks quite odd because, like, you know, there's a bit above the function, there's a bit below the function. So I'm going to ignore option A. It looks like option D is also a little bit odd. Could still work though. So, but I think option B and option C are like my most likely candidates at this stage. So I want to find the area between them, right? If I want to find the area between two curves, so if I want to find the area between f of x and g of x, the area between those curves is going to be equal to the integral of f of x minus g of x with respect to x. And if we want things to be done like neatly, this should be the top one, the one on the top, and this one should be the one on the bottom. So going back to my thing, the red one here is the second function. So the top function when I draw it is 2x squared plus 1. That's my top function. And then we're subtracting our bottom function, which is 3x cubed minus 2x. Make sure you subtract the whole lot with respect to x. So the integral of that should be equal to the areas between the reds and blues. Alright, I've typed it all in. Normally you'd like simplify it or something, but there's no need. We're just calculator, we're doing multiple choice. No need to like get rid of brackets or anything. Alright, drawing it. This green one here is, so this green one tells us the area between the red and blue at all these points, right? Okay, so from here, what can we do? So with all these graphs on, sometimes it can feel a little weird, but the way that we can do it is G-solve, integral, and then find the integral here. Then you just got to be careful because it asks you to select your graph. Make sure the correct graph, the green one, is flashing. enter. And then just choose, I think it's one of these two, right? For the reasons I mentioned earlier, there's these weird intersections. Let's just try this one, say 0.356. Okay, and the area there is 0.5007. Super, super close to 1/2, which is what we wanted. 1/2. That's our answer. You might double check by doing some other ones, but that's our answer. Very, very close to 1/2. Happy days. Calculator stuff. Boom. Next question. All right, have a try at this one. Got a little bit of a theme going here today. We got some integrals and stuff. We've got a probability density function here between 0 and 1/2. And we're being asked to find the median value. So what does that mean? Well, reminder from earlier. A probability density function has an area under the curve of 1. Now, the median value is some mystery line here, right? Maybe there, such that the area under there is 0.5 and the area under there is 0.5. There's our median. 50% of x values are this side and 50% of x values are that side. Or 50% of whatever it is, it takes this x value, and 50% of whatever it is takes this value. So we could do what we've done just now and graph that and like do some trial and error with these values. But let's take a different tactic. So we're saying that the integral is going to be equal to 0.5 between something and something. Now, notice that our thing here is between 0 and 1/2. So between 0 and k is going to be this value right here. 20x 1 minus x cubed with respect to x. So there's our setup. We should be able to kind of just solve this on our calculator. So let's make sure we do it right. We've got to go math, wrong straight away. Options, calc, solve n, and then we type in exactly what we see here, 0.5 equals, and then we're going to need, I think we're going to need some math stuff here. Calc, there it is, integral, and then we're integrating between these values. So we're integrating between 0, and you can type in just the letter, well, any letter you like. Let's use the letter I, alpha, k. So I'm going to type the k in there, and then type in your equation, 20x bracket 1 minus x, close that bracket to the power of 3 with respect to x. Now you're going to need one more thing here, right at the very end, can't get there, comma, and then the value that you want to solve for, alpha k. And then we'll close that bracket up. That last bracket's closing up the what we're solving. Really hope I've done that right. All right, warning, always a warning. Okay, there are two answers here. Negative 0.18, which is outside of our domain, and 0.31381. 0.3138. So our answer is D. Now, of course, you could now graph this and then find the integral between 0 and 0.3138. And I'm feeling super confident your answer will be 0.5. All right, celebration time and on to the short response. Okay, so question 15, have a try, see how you go. Alright, so a puddle after a storm is slowly evaporating. So we've got a puddle here and the water's going away. The depth of the puddle after 2 p.m. is given by this function here. Okay, determine the average rate of change in the first 30 minutes. Alright, average rate of change, that's an important idea. We've got a function, we'd be mad not to sketch it given this is a tech active exam. Alright, so there's my sketch here. Obviously, I typed it in there, but you don't need to watch me type that in. Okay, so what's going on? Well, I might just do a quick trace just to get a sense of what's going on here. Okay, great. So at about time 0, because this is time on the x-axis, on the y-axis we have a depth of 1, right? At time 0, 1. And then we keep going down here a little bit. This is half an hour into it. Remember, the time is in hours here. And so we can keep going on here. Okay. Now, it says, determine the average rate of change in the first 30 minutes. So if you've got a graph that looks like this, the average rate of change between 2 points in the first 30 minutes, it's the gradient of that line. So don't make the mistake here of thinking you've got to do derivatives and things like this. If it says average rate of change, you've instead got to find, like year 9 maths, you've got to find the gradient of that line right there. Okay, in other words, it's going to be, part A is going to be average rate of change is going to be equal to y2 minus y1 over x2 minus x1. Okay, now this point here is of interest to me, and that's 30 minutes, because it says in the first 30 minutes. Now, on our graph here, not 30 minutes, 0.5 hours. They always do this. They end up writing an equation in hours and then asking you about minutes or vice versa. And then we got this point here. So if I call this point y2, x2, and this point x1, y1, like that, I just need to know what all these values are. Okay, I know what x2 is. It's 0.5. I know what x1 is. It's 0. I know the other bits that we can do here is probably through like some sort of G-solve, and I think it's called a Y-calc, where I type in the x value and it will give me a y value. So when x equals 0, y equals 1, so that's my y1 here. And then we do another one of those y-calcs, or x-calcs, sorry, y-calcs, and x equals 0.5. Okay, and I get 0.8824. That'll do. So this equation, if I figure this out, I'll know my average rate of change in the first half an hour, the first 30 minutes. All right, so you know I love my dodgy little calculator here for doing this kind of thing. Negative 0.2352. And then we really want some units for this. So this, we've got to use the units that we've been given. So it's actually changing at a rate of this many centimeters, because we're told that the depth is in centimeters, I think. Well, now we do, anyway. So let's go with centimeters per, and then the time is in hours. All right, so what does that mean? It's going for the first 30 minutes, it's going down at a rate of 0.23 centimeters per hour. Okay, so that's part A. What about part B? Determine the change in depth over the second hour. This seems relatively straightforward. This seems like we're just going to do another couple of those y-calcs, because this graph continues on. This is hour 1. This is hour 2. And so we're just finding out how much the depth has changed from here to here. So let's pull our calculator back up. So for part B, the total change across that second hour is going to be equal to, I don't know, let's go with the value here first. So after 1 hour. So that's 0.6065. And then the value after the second hour. So another one of those. 2 hours. So 0.1353. And then calculate that. So the total change, 0.4712 centimeters. So it's gone down by about half a centimeter across that second hour. It's never a terrible idea to just look at your picture again one more time before you finish up and move on. This is 1 centimetre. Or down here is 0 centimetres. You can see by the time we get to like 3 hours, nearly the whole thing's finished, right? So between 1 and 2, it looks like we're losing about half of our depth. Maybe not quite half our depth. So it just feels right. I like what I'm seeing there. So, okay, great. Part B, done. Part C. Determine at what time the rate of change is greatest. All right, so let's try to use our calculator here and work through it. Now, we know, I'm just sort of starting again here, part C, we know that this is our depth formula. Depth with respect to t, e to the negative t squared on 2. We're being asked, when is the rate of change of this greatest? So, in other words, like, when is, and I'm going to write in words here, when is d dash t at maximum? All right, so that's my question to myself. Because if I know when d dash t is at a maximum, when the derivative of that, the rate of change of that is a maximum, that's when it's happening. All right, so now I'm going to go to my calculator. And this function here, I'm going to put it in one more time, but this time I'm going to do some, now where are you? I think it's calc. There it is. I'm going to do the derivative of this function right there. Okay, so I've typed that in. It's going to be our red function when we actually draw it. Okay, great. Determine at what time the rate of change is greatest. You can see that my red function here has a minimum, right? Has a minimum right there. Now, what I will do here for my examiners so they can see what I'm doing is I'm going to do a sketch. This is d dash t, right? And so it's the rate at which it's changing is greatest here. I know you're looking at that saying, well, that's a minimum, but we're talking about a rate of change of the depth of this puddle, right? So the magnitude of the rate of change is greatest here. I think that's how we should interpret this question. All right, so we can do a G-solve. We can do a minimum, maybe. I've got to choose my graph again. And I get this value right here. X 1.0000007. I think we can round here and we can say max rate of change at time equals 1. Okay, that's it. Determine at what time the rate of change is greatest. It is at time 1. And that makes sense looking at our blue function. I like sketching them both together. Look at the gradient of our blue function at 1. That's when it's steepest. And that's what we're expecting to see there. Okay, we can celebrate and move on. Okay, have a try, see how you go. So we've put this question in here because you've got to be able to look at a probability question and determine what is happening. Is it binomial, is it normal distribution, etc. Okay, this person's going to the store with their broken iPhone. There are 4 people at the store. 1, 2, 3, 4 people at the store. And they each have a 20% chance of being available, and their probability of availability is independent of the others. So discrete things, each having the same probability, 20%. Binomial, feels binomial. If you speak to a worker, there is a 65% chance that they will give you a new iPhone. Given that you will only walk into the store if at least one of these people is available, what is the probability that you receive a new iPhone? So you walk past the Apple store, you look, they're all busy, you walk away. If at least one of them is available, you're going to walk in. Okay, let's find out. So we want to know the probability that at least one of these people is available. Now, thankfully, we're going to be able to put this straight into our calculator. All right, so we're going into statistics mode there, and we're going into distributions, binomial distributions. Use a BCD here. All right, so we want lower value of 1, at least 1, up to 4, right? We don't care if everyone's available, that's also great. Number of trials, there are 4 people that possibly could be available, and the probability of success for each one is 0.2, the probability that they're available. Boom. Okay, so the probability that x is greater than or equal to 1 is 0.5904. This is the probability that you will walk into that store, right? That's the probability that you'll walk in and talk to someone. Now, what is the probability that you'll actually get a phone? Probability of getting a phone. Well, that's going to be equal to the probability that you walked in, 0.5904, times the probability that, given that you've actually talked to someone, that they will give it to you, 0.65. Okay, and type that into your calculator. Final probability of 0.38376. The probability that you'll receive an iPhone here is 0.38376. Then, not tricky maths here, obviously. The tricky bit is being able to read this question, because there's a lot of different words in there, and being able to interpret, is it binomial, is it normal? Some questions end up being both. This question was binomial probability, and then just like a multiplication principle. So, 2 kind of ideas here in the single question, even though there's just not a great deal of maths there. Celebrate! So that's been part 6, only 2 more to go after this one. Thank you, as always, to my friends here. As mentioned at the start of the video, you could be as cool as those people. Just head over to the website, click the link, and maybe sign up, join up, become a tutor. Catch you in the next one.